Oops. It's on the other screen. What? Sorry. So, hello everyone. Welcome back. I hope you enjoyed your lunch. If unfortunately not, I hope you'll enjoy the following presentation. So, in the lecture, in the previous lecture, my colleague already covered the DRAM scaling issues related to retention. So now we will look at another aspect of DRAM scaling related problems by starting with a very curious phenomenon. So modern DRAMs, they are prone to disturbance errors. So for example, we have a DRAM array here. The DRAM cells are organized in rows. And if we repeatedly open and close one row, which we call aggressor row, or in a more illustrative term, the hammered row, we will induce disturbance errors in nearby rows, which we call victim rows. And if these disturbance errors accumulated enough, then they will cause Bitflips in nearby rows. And apparently, by doing so, you can induce such redisturbance-induced Bitflips in most of the real DRAM chips you buy today, as pointed out by this ISCA 2014 paper. So here's a very simple proof of concept program on how you can do this on a real system. So you just repeatedly access to memory addresses, let's say X and Y, and then you flush them from the cache to make sure that you are indeed accessing the DRAM itself. And then you use an M-fence to make sure the accesses are complete, and then you just keep doing it over and over again. Then you can induce Bitflips in the DRAM rows that are adjacent to the DRAM rows that pointers X, the memory address X and Y point to. So the implication of this is very severe. So apparently you can take over an entire system with just a single Bitflip. So after the initial demonstration and disclosure of the RowHammer problem by this ISCA 2014 paper, a security team from Google Project Zero, they successfully demonstrated that you can leverage RowHammer to gain full kernel privilege. Since then, there are many more works in the security domain where people try to leverage RowHammer to do many different kinds of attacks. So for example, you can do it from the browser with JavaScript. You can do it remotely using RDMA. You can even use the characteristics of RowHammer Bitflips, not to control the system, but to infer the data values stored in the memory locations that you don't have access to. Some recent works even investigate the implications of Bitflips on deep neural networks, and they show that if you're able to flip just one bit in the weights, then you can cause detrimental performance degradation in some vision tasks. So I believe there are much more security implications to this if you can just arbitrarily flip bits in your memory. And in fact, even up to this day, people are still proposing and demonstrating many attacks using RowHammer. So to approach this problem, so we have two major directions. So first, we need to have a good and fundamental understanding of the RowHammer phenomenon, the characteristics of the Bitflips, and how will they have any architectural or security implications to our systems. And then the second direction is to leverage these observations, these insights, this knowledge to propose flexible, efficient, and secure mitigation techniques to protect us from RowHammer. So in this talk, I will be focusing on the first part, which is understand the RowHammer phenomenon itself. Yeah. So to start with, we look at the first paper that discloses and demonstrates RowHammer. This is published in ISCA 2014, exactly 10 years ago. So back then, we used this kind of infrastructure that my colleague already briefly introduces. So it consists of a host machine that controls an FPGA-based DRAM characterization platform that we put the DRAM module under characterization to, so that we can have fine-grained control of the DRAM commands and timings that we send to the DRAM. And the entire setup is also in a heat chamber, so we can precisely control the temperature. So this first RowHammer work covers a lot of DRAM modules, ranging from a wide range of vintage, so from 2008 up to 2014. So this paper covers the the 7 most important characteristics of RowHammer, which we will briefly discuss. So the first, or let's say the most important takeaway would be that most DRAM modules are vulnerable. So back then, they tested the DRAM modules from all 3 major DRAM manufacturers, and they find that the vast majority, let's say over 80% of the modules are vulnerable, and they can induce tens of thousands of bitflips in a module. And second, they find that the DRAMs that are, let's say, manufactured more recently, they're significantly more vulnerable to older DRAMs. So as we can see here, the x-axis is the model vintage, and the y-axis is the number of errors. We can clearly see that as this red band in the plot shows. After, let's say, a certain year, almost all the modules are suddenly very vulnerable to these RowHammer vulnerabilities. And they have many bitflips, and it seems that the newer the modules are, the more vulnerable, or let's say, the more bitflips they experience. And the next aspect we look at is the spatial relationship between the aggressor rows, which is the row that you keep accessing and hammering, versus the row that shows bitflips. So this is the original result from the paper. Let's say our aggressor row is at row 0, and then we see the bitflips at row offset ±1, and those 2 rows have the most bitflips, which makes sense because they're the physically adjacent rows. But we also see some other rows that, let's say, are not, let's say, adjacent to the aggressor. So does anyone have any hypothesis or idea on what could be the possible reasons for this? Any guesses? Excuse me? Harmonics of the frequency. That's an interesting take. But what does frequency mean here? toggling rate. So let's say, yeah, like this experiment is conducted that, so we just hammer, let's say we take one sample row, we hammer it with a fixed amount of times. Like the toggling rate is the same, but we still see, let's say, bitflips on the rows that are further apart from ±1. So yeah, of course, like one very direct hypothesis is that, so this RowHammer effect is not local. It can affect rows that are, let's say, more than ±1 offset away. So yeah, that's one hypothesis. Any other idea? Okay, if not, then yeah. The second explanation to this could be that what we perceive as adjacency, let's say if the row addresses are ±1 away from the aggressor row, so this logical adjacency does not necessarily translate to physical adjacency. So it's known that inside the DRAM chip, due to certain reasons, it could be the design of the row decoder, it could be that the manufacturers are deliberately obfuscating the relationship between logical rows or physical rows. But the end result is that the logical row address does not necessarily like have a sequential or like a trivial mapping to the physical row locations inside DRAM. So if your logical adjacent rows are not actually physically adjacent, or vice versa, the physically adjacent rows are not always logically adjacent as it appears to your memory controller, to your processor, to your system, then we can also see some effects like this kind of like non-adjacent victim effect. So if you look at this, there's like like small peaks at like about -7 and +7, but like there are almost no at like 2, 4, 5, 6. So this probably hints that, yeah, the non-trivial row mapping can be another important factor that affects these information. And if you think about this, like this can have impact on those people that does the actual attacks. So if you can correctly figure out the mapping, then you're sure that you're attacking the directly adjacent rows, then you will probably have more bitflips. Yeah. Yeah, and of course, like in most cases, if there's like no complicated mapping, you will see most of the rows affecting the directly adjacent two rows. The paper also investigate, as someone mentioned before, the toggling rate. So on the x-axis, we have like access interval to aggressor. This is essentially like the toggling rate, like how long you wait between activations, and the y-axis is the errors. And we clearly see that with the smallest interval or the highest toggling rate, or in other words, we see like the highest activation frequency, something like that, you have the most errors. Yeah. And they also investigate. So because DRAM stores information as electric charge, and by hammering it, you'd like just accelerate charge loss. So if you refresh it more often, such that even with the highest, let's say, toggling rate or activation rate, you cannot cause enough charge loss, then you can effectively, let's say, mitigate this problem. So they do a sweep of the refresh interval. So here, this actually means the interval between a row is refreshed first and the second time. So it's actually like called refresh window in some JDEC documents, but yeah, you got my meaning. So at the, let's say at the nominal refresh window of both DDR3, DDR4 memory, it's 64 milliseconds, we see a lot of bitflips. And if we keep reducing the refresh interval, we see that like we only get rid of this issue if we refresh the rows every 16 milliseconds. That's actually like a large, like a very large increase in your refresh frequency. So it will have a dramatic impact on both the performance of your memory system and the energy consumption. Yeah. And then they also investigated the data pattern in the aggressor and the victim and how they affect the errors. So on the left, they tested like some simple patterns. Solid means like all the both the victim rows and the aggressor row, they have the same data. And then they also tested some alternating patterns. In here, we call them row strip, which means like the aggressor and the victim, they will have opposite data values. And people find that by having the aggressor and victim having opposite values, you can induce many more bitflips compared to the trivial cases where the aggressor and the victim, they have the same value. So this means that the RowHammer phenomenon is data pattern dependent, and this also hints to, and it also provides some insights for the device level mechanisms of this phenomenon. There are also other minor observations in the paper. Let's say the RowHammer victim cells, they are not necessarily retention weak cells. Those cells are like the cells that will just like leak a lot. So there are like almost no overlap between them. This hints that the RowHammer vulnerability, the physical mechanism is likely different from the failures caused by the retention leakage. And the errors are very repeatable. This means that if you can successfully induce bitflip at a certain cell once, then very likely you can reliably keep doing so. So this makes attacks leveraging RowHammer practical, because you can do something like a memory templating, that you can find the bits that are vulnerable beforehand, and then you're confident that, okay, if the victim places the sensitive data in those places, then you have a high chance of flipping those bits. And there can be like more than one bit flip in a cache line. So this makes the simple ECC solutions in memory, let's say the SecDet, single error correction, double error detection scheme, not 100% secure against both preventing and detecting these errors. Basically, like if there happens to be 3 bits that flip in a cache line, then you don't even know there are bit flips. And finally, they find that if you sandwich a victim row between 2 aggressor rows, then you can induce RowHammer bitflips much more effectively. So this translates into both. You can see the first RowHammer bitflip with much fewer aggressor activation. So in fact, like with 2 aggressor rows, you need much less than twice the number, you need much less than 50% of the aggressor activations in a single-sided case to induce bitflips. So later, some device level works, they actually finds out that by sandwiching a victim row in between 2 aggressor rows, there are some silicon level mechanisms that accelerates the charge leakage fundamentally. So yeah, and on the other hand, if you hammer them long enough, you will see many more bitflips compared to just using a single aggressor row. So this also means that the RowHammer vulnerability is also related to how you access the memory. Yeah. So now we have the issue. So we want to find some solution. So the 2014 paper, they investigate two categories of solutions. One is kind of like some immediate patch. We want to make the DRAM chips that are already manufactured, are already deployed in the field, secure, but it's hardware, so you cannot like just easily roll out patches. So the solutions are limited. And as we have shown before, the simplest one is just to let's increase the refresh rate of our system. And in fact, that's what a lot of the companies, the industry do after they're aware of this issue. They roll out like, let's say, BIOS updates that changes the timing parameter of the memory controller so that the memory modules are refreshed much more often. But if we want to solve this issue fundamentally, then we have to think about the design of both the memory controller and the DRAM chips. So the EFCL 2014 paper, it proposes a very simple but also very effective solution called Para, and very soon after it's it already sees its adaptation in the field. So and as I said, like this is an example of some short-term solutions that got adapted by the industry by just increasing the refresh rate. Yeah. So the proposed solution in the paper is called Para. It stands for probabilistic adjacent row activation. So the key idea is very simple. So whenever we close a row, and remember that if we want to access another row in the same bank, we have to close the currently open row first. So when we want to close a row, we roll a dice, and with a very small probability, let's say 0.5%, we will refresh the adjacent rows of the rows that we have just closed. So the key idea behind this is that because in RowHammer, you need a very high toggling rate. That means like you activate the rows in a bank many, many times. Then this small probability will kind of like pseudo guarantees you that your victim row will eventually be refreshed. And by tuning this probability with the minimum number of time that you need to activate a row to induce Bitflips, you can have some pretty strong security guarantee. And the paper shows that if you set P equals 0.5%, and if the let's say the RowHammer threshold, which is like the minimum number of row activations you need to do to induce a Bitflip, is 100K, then you will only get like 9.4 times 10 to the power of minus 14 bits flipped in a year, and I think that's a pretty strong guarantee. Yeah, and of course, by varying this P, like it kind of becomes like a knob that you can tune to balance between the security guarantee and the performance of your memory system. So the advantages of Para is that it's very simple, it's stateless, and it's kind of like security guarantee can be mathematically proven. So it's effective and low overhead, and that's why it's like very soon adopted by the industry. So there are two ways to implement Para. One is that we can implement it in a DRAM chip. So this is kind of like that some of the DRAM manufacturers, they already, let's say, covertly do. So this requires you have enough slack or headroom in your timings so that you can sneak in those extra victim row refreshes when you close a row, let's say. But as we have seen before, there are plenty of headrooms in the timing parameters, both governed by JDEC and published by the manufacturer. So that's how some of them do it. And if you want to, and like of course, like a simpler way would be to implement this in a memory controller, which doesn't require changes to the DRAM chip, and the victim row refresh can just be implemented as like regular activations to the victim rows. However, this needs coordination between the memory controller and the DRAM, especially the controller needs to know which rows are physically adjacent. And this goes back to the earlier adjacency discussion that we just had. Because of those the existence of those non-trivial mappings, and yeah, this becomes a challenge in implementing para in the memory controller, because basically, if you don't even know what are the adjacent rows of the aggressor row, then you could be doing useless victim row refreshes. Yeah, and here's an example of something like para implemented on a real system. I'm not sure like if the text are readable to you, but this is like a ThinkPad laptop. In the BIOS, you can enable hardware RHP, which is how Intel calls para, or choose to double the refresh rate. And of course, you can tune the probability of the victim row refresh. Okay, so that's kind of like the story of like the infant age of the RowHammer phenomenon. So is there any question? If no, yeah, then yeah, please.
Yeah, so how does this work with the refresh rate that we saw earlier for data retention? Is it one or the other, or they work together?
Theoretically, you can combine these, right? Because increasing refresh rate, it's like orthogonal to let's say add victim row refreshes. But I think in practice, I don't think it's very practical to just like blindly, let's say double or even quadruple your refresh rate. Because by refreshing that many often, you really pay a lot in the performance loss, the availability of your memory module, and also the extra energy cost. And that's also why like both industry and academia, after realizing this problem, they're all working on mitigation mechanisms that let's say tracks the activation of the rows, and then they can choose to only throttle, block, or the aggressor row, or to refresh the victim rows. That's much more economical or practical compared to just blindly increasing the refresh rate. Yeah. Thank you. Yeah, please.
I don't have a lot of background on memory, so I don't know if this is a stupid question, but if I understood correctly, your camera row was constantly accessing memory address.
Yes.
So in yesterday's lecture, they told that there's this like row buffer.
Mm-hmm.
So if the first time you activate your row,
mm-hmm.
the second time you don't activate your row and move the row buffer.
Mm-hmm.
So this works because there's a way to bypass this.
Yes. Yes. So if we look at like the simple code that people use to demonstrate this phenomenon, so here like we actually use two memory addresses, and let's say these two addresses are in the same bank, and there's a high chance that they belong to different rows. So if they are in different rows, then and also in the same bank, then you have to close the previously open row in order to access the other row. So you just like keep ping-ponging between the two rows, then you are making sure that you are doing the real row activation.
So you always have to access two rows.
So in a real system sense, because there's like a design in the memory controller called row policy that basically decides what you would do after opening a row. So for performance reasons, memory controllers tend to keep a row open a bit longer after it's accessed. So because of this, like if you only access one row, then there's a chance that the second time you access that address, the row is still open. Then you're not like making a lot of activations. But if you access two rows in the same bank, then the previous row has to be closed. So then by doing so, you make sure that you are generating extra activations. Yeah, thank you. Very good question. Yeah. Okay, if no further question, then let's look at the next item. Yes. So as we discussed, the first disclosure and demonstration of RowHammer is in 2014. It's already 10 years ago. So what has happened in between these 10 years? So at around 2020, we published a paper called Revisiting RowHammer, because during these 10 years, DRAM has changed a lot. We moved from DDR3 to DDR4. We have the emergence of mobile devices, so LPDDRX devices. They also become like very important. And as with all of these is the continuous scale down of the DRAM technology node. That's how the industry can pack more and more bits in like roughly the same size of the small chip. And we already seen before that there's kind of like a Bitflip versus vintage issue in RowHammer, that the newer the module, the more vulnerable it is to RowHammer. So it's natural to revisit this after the DRAM design has significantly shrinked to achieve much higher storage density, and that's exactly the motivation of this work. So this work investigates like an even larger population of DRAM chips, 1,580, and they find that, not surprisingly, newer DRAM modules are more vulnerable to RowHammer. That means you will have many more bitflips, and you can see the first bitflip much earlier than previous generations of memory. And to have some, to be specific, there are certain DRAM modules, some newer LPDDR4 chips that shows bitflips only after 4,800 activations to an aggressor row. So if you think about the numbers from the 2014 papers, like 100K, 15K, that's like orders of magnitude reduction in how fast you can see the first bitflip. They also show that, again, not surprisingly, with newer DRAM technology, you see these bits flip in more rows and sometimes farther away from the victim row. And we already discussed there can be multiple reasons for these like non-adjacent victim effect. And as a result of like this very significant increase in the RowHammer vulnerability, some previously proposed mitigation mechanisms did not guarantee to be secure or effective against these like latest threats. So this work specifically investigates DRAM chips across multiple generations, old DDR3 chips, new DDR3 chips, old and new DDR4 chips, and very dense LP DDR4 chips that are, let's say, in the tens-ish nanometer of process node, and they investigate chips from all three major DRAM manufacturers. So the first thing they look at is how hammer count, or let's say the minimum number of row activations you need sorry. So like they look at, let's say for a given hammer count, how many bit flips you can achieve for these different generations of DRAM chips. So on the x-axis, it's the hammer count. On the y-axis is the number of bit flips. So to the upper left corner of the plot, this means a much higher vulnerability to RowHammer. And if we look at this in general, the more advanced the process node is, like the curve tends to go to the upper left corner of the figure. This means that it can have more bit flips even with smaller number of hammers. So this shows that the RowHammer bit flip rate increases with the process node of DRAM. And then we also look at so how many hammer count you need to induce the first bit flip in the chip. So the x-axis this time is like different generations of DRAM, and y-axis is the minimum number of hammers you need to induce the first bit flip. And again, in general, the newer the technology node is, the more vulnerable you are to RowHammer, because you see the first bit flip with much fewer activations. Yeah, and here we see that this like 4.k minimum activation count number.
May I ask something?
Yeah, sure.
What's the difference between LPDDR4-1X and LPDDR4-1Y?
So they are like the kind of like the code names to different process nodes. So 1X is like kind of like the first generation when the process node goes below 20 nanometer, and 1Y is like the generation after it.
So it's the same standard but a different process.
Yeah. So the chip, the architecture, the interface, the speed, those things, the voltage, they follow the same standard. But yeah, the manufacturers, they keep optimize the manufacturing technology so that they can pack more bits, save more power. And so like the same 1X can have, let's say, different actual technology across manufacturers. Those are like a highly sensitive thing that we cannot always know. But within the same manufacturer, like 1Y is like one generation newer than 1X. So that's like why we see, let's say from manufacturer A, 1Y has much fewer, it needs much fewer activations to induce the first bit flip compared to to 1X. Yeah. Yeah, thank you. Okay, then with this information, so we revisit these some of the previously proposed RowHammer mitigation mechanisms. So on the x-axis, it's like the minimum hammer count that you need to induce the first bit flip, or in other words, that's like how aggressive the mitigation mechanism has to be configured in order to guarantee the the robustness security of this system. And the y-axis is like a normalized slowdown of the system, because you need to pay extra cost to refresh the victim rows. So the more often you refresh, let's say the more aggressive your mitigation mechanisms is, then you pay more of the performance penalties. So as we can see, the oops, it's I don't think you can see my pointer, right? But like, yeah, like the leftmost steeply decreasing curve, that's the performance penalty of increased refresh rate. And you can see like it, you already like lose about 30% of your system performance, even to protect against RowHammer for some old DDR3 modules. And this is definitely not scalable, as RowHammer kept getting worse for newer DRAM technology. So this, and we also evaluate an ideal mechanism. So that is kind of like an oracle that it has like infinite capability to track and count which row are activated the most, or let's say like it will just know which row is the RowHammer aggressor row, and it will only refresh the victim row if the row, let's say if the aggressor row is guaranteed to activate more than the RowHammer threshold. So that's kind of like the performance upper bound, and this is kind of like the green line on top of the figure. Yeah, and we show that there are significant performance headrooms between, let's say, some of the proposed solutions. For example, Para, like it's the black line that we highlight its distance with the ideal solution with, as the projected RowHammer threshold kept decreasing. So this kind of shows that there are still significant opportunities to design better, more scalable RowHammer solutions, which my colleague will cover in the next part of the lecture. Yeah. So by far, so is there any question about revisiting RowHammer? Okay, cool. So yeah, then we move on some deeper analysis of the RowHammer phenomenon itself. So because RowHammer is like a physical phenomenon that actually happens inside the silicon of a DRAM chip, it surely has to be affected by many other external parameters. So in this paper called Deeper Look into RowHammer's Sensitivities, we specifically look at the three following fundamental properties related to the RowHammer vulnerability. First is the temperature of the DRAM chip. Second is how long you keep the aggressor row open. And third is the location, the physical location of the victim DRAM cell. So yeah, for temperature, I think this is actually like a quite important aspect to look at. So some people might think, okay, like I will only run my DRAM in a well-ventilated, well-cooled data center, so my DRAM will always remain cool. Yes, like if you only use DRAM in your data center, it's well-ventilated, well-cooled, it's true. But as the industry kept moving forward, there are different ways of integrating DRAM to your processor, let's say. So these days, like HBM are very important. And the way HBM like integrates with the processor is very different than let's say in conventional data centers where we plug DRAM as DIMM modules to like as isolated DIMM modules to the motherboard. So let's say for HBM, it's tightly packaged together with the let's say the processor die. And in most cases, they might even share the same heat spreader. So this means that, like, yeah, if your processor gets very hot, which is very common, then your DRAM chip will also get very hot. So that's kind of like the reason why I want to study temperature. And second, aggressive row active time. So this is an interesting thing because, like, as we discussed and investigated in the first RowHammer paper, so people there care about the toggling rate, the activation frequency. So yeah, they want to see like how fast I can activate, close the row. But they don't, let's say, quite look at what if I, let's say, make a row stay open for a longer period of time. And as we discussed, the memory controller has a lot of reasons to keep the row open for a longer period of time, mostly for performance reasons. They want to increase row buffer hits. Then what's the effect of this? So what if we kept the row open a bit longer instead of like just closing it immediately to get the highest toggling rate? Yeah. And the third, yeah, the physical location of the victim DRAM cell, yeah, that's just like a very natural thing to look at. So let's look at the key results of this paper. So we characterized like 272 DRAM chips from some like 4 major DRAM manufacturers. There are many takeaways and observations. And the most important 3 results from this paper is the first, RowHammer Bitflip likely to happen in a bounded range of temperature. In other words, like if the temperature, let's say for a given RowHammer Bitflip at a cell, if the temperature is low, it's less likely to happen. But if the temperature is too high, then it's also less likely to happen. And second, if you keep the aggressor row open for a longer period of time, you will have more bitflips. And third, so the RowHammer bitflips or the RowHammer vulnerability is like not uniformly distributed across the chip. Certain locations in the DRAM bank, they're more vulnerable to RowHammer attacks. And based on these observations, so the paper gives some insights, so directions on how people can both craft more effective attacks and design more effective and efficient mitigation mechanisms. So let's take a deeper look at these results. So first, like we test, again, many different chips. This time, like we even included like the Force manufactured Nanya. Yeah. And we show that, so if you keep an aggressor row open a bit longer, that is to say, like you are not trying to activate the row as frequently as possible. So as the figure shows here, like in old days in RowHammer, we want every row to be closed as early as possible so that we can activate the other row as fast as possible. But what we do here is we keep a row open for a longer period of time, and we kept it open. And we kind of do this, and we see you need much fewer aggressor activations to induce the first bitflip. So this has implications on mitigation mechanisms that relies on, let's say, a fixed like RowHammer threshold value that are obtained and characterized with the old RowHammer pattern in mind. Because yeah, like in this new attack, you can just like keep every row open a bit longer, and then you will trigger a bitflip with fewer activations than it is needed to trigger the mitigation mechanism. Yeah. And second, we look at the spatial variation of the RowHammer threshold across different rows in a bank. And we see that there are like a huge difference in the, let's say, the highest RowHammer threshold and the smallest RowHammer threshold we observe in a chip. It can be as high as 2x or even 3x as shown in this figure. Yeah. So we conclude that the RowHammer vulnerability significantly varies across DRAM rows. We also look at how different columns of the DRAM are more vulnerable to RowHammer. So here, this heat map shows on the x-axis is the column ID. The y-axis is like just like different rows, and the lighter the color, or let's say more to the reddish, yellowish the color, then the more vulnerable the column is to RowHammer. So we observe that certain columns, as you see, as the bright strips in this heat map, certain columns are more vulnerable to RowHammer than the others. Yeah. So with these different spatial variation in mind, it can have some implications to help design more effective mitigation mechanisms. So let's say from the characterization result, we can see that only 10% of the rows, they are very vulnerable to RowHammer, that they require a very low number of aggressor activations to induce the first bitflip. And let's say, yeah, the rest 90% of the rows, and they need twice the number of activations to induce a bitflip. Then your mitigation mechanism can leverage this, let's say, heterogeneity in RowHammer vulnerability, that you set different aggressiveness for different parts of the rows that have different RowHammer vulnerabilities. And we recently actually published a work that does a more detailed analysis on this spatial distribution and variation, and perform a detailed quantitative study on how this can improve the system performance when there's such intelligent mitigation mechanisms implemented. Yeah. So here's the full talk video. There are many observations that we cannot pack into the presentation. So if you're interested, you can watch this video. So now we are in 2024. It is another 4 years after the revisiting RowHammer work. So we ask, in today's latest systems, are we getting rid of the RowHammer issue? So that's kind of the currently active research, and the answer is no. So we also have a recent work that will appear in DSM 2024 that we look at the RowHammer or Redisturbance in more general in HBM2 chips. And we have an archive version. If you're interested, you can take a look. It also has some more interesting detailed analysis on the spatial distribution of the RowHammer vulnerability. One very interesting one in that is that we find that DRAM rows on the edge, on the two edge of a subarray, they are less vulnerable to RowHammer than DRAM rows in the middle of a subarray. That's a very interesting phenomenon. Yeah. So another aspect that we look at RowHammer, or let's say redisturbance more general, is illustrated in this work. It's called, it's published in last year's ISCA. It's called RowPress, Amplifying Redisturbance in Modern DRAM Chips. So remember that like in the previous work, we talked about how the time that the aggressor row is open will enhance the RowHammer vulnerability. So in this RowPress work, we kind of dig deep into this interesting phenomenon. So let's say back then, yeah, we just think, okay, it's just like another aspect of RowHammer. If you keep a row open longer, then your RowHammer vulnerability will be worse. But by looking this like aggressor row open time aspect in detail, we're actually able to recover that this increase in aggressor row on time is not only RowHammer, but it leads to another kind of completely different error mechanisms in DRAM. So that's like why we call this work RowPress versus RowHammer. So in this work, we demonstrate and analyze RowPress. It's another redisturbance phenomenon that causes bitflips in real DRAM chips, and it is different from RowHammer. So we show that it's different, and we even demonstrate in a real system that if you use if you leverage this RowPress vulnerability, you can use a user-level program to induce bitflips much more effectively compared to using RowHammer on real DRAM chips that already has the industry's RowHammer mitigation implemented. And we also propose effective solutions on how to mitigate RowPress. So RowPress is a phenomenon that we find that if you keep a DRAM row open for a long time, it will cause bitflips in adjacent rows. And these bitflips, they do not necessarily require as many row activations as RowHammer. So in extreme cases, we find that if you activate the row only once and you keep it open, yeah, please.
How long is too long?
So yeah, that's what I'm going to talk about next. Yeah, thank you. But that's a very good question. So yeah, in extreme cases, we show that if you open a row just once and keep it open long enough, you can induce bitflips. So.
And also discharge that row.
And also discharge the row that is active. Which row is active?
So you have kept the row open.
Yes.
You discharge that row and also introduce bitflips.
So yeah, the bitflips are only in the victim row. So in the aggressor row that we kept open, there will be no bitflips because because the open row is kind of like backed by the sense amplifier. So its charge level will always be maintained. So the victims, the bitflips are only in the victims that are like adjacent to the aggressor row. So yeah, we've already seen RowHammer. So if you keep opening, closing this as fast as you can, you induce bitflips in the neighboring adjacent rows. So and it was very well studied for 10 years, and most of the mitigations, as we discussed, they kind of work by detecting if there's like a high number of activations to a certain aggressor row. So what if this other redisturbance phenomenon, it does not rely on high row activation count? Then yeah, there will be severe security implications that many of the existing mitigations that tracks and counts row activation time only, they can be just like very easily bypassed. So instead of use a high activation count or like activate the DRAM row as frequently as possible. So RowPress significantly increases the time that the row stays open. So for example, in RowHammer, you can so you keep a row open only for the minimum amount of time allowed by the standard, let's say 36 nanosecond, and then you need 47,000 activations to induce the first bitflip. But if you keep the row open for 7.8 microsecond, that's kind of like the maximum amount of time that you can keep a row open as the JDEC standard specifies. Then you only need 5K activations to induce a bitflip. That's like an order of magnitude reduction in the number of aggressor activations you need to induce a bitflip. And in extreme cases, let's say if we go beyond the JDEC standard, if we let a row stay open for 30 milliseconds, so this is beyond the row open time limit in JDEC, but it still falls within the, let's say, the refresh window of DDR4 chips, which is 64 milliseconds. So we are only using half of that. So with this, if you activate the row only once, you can even induce bitflips. So this already shows that, yeah, this phenomenon, it's not RowHammer. We don't rely on high number of activations. It's the amount of time that the row is open matters. Yeah. So again, we use DRAM Bender or SoftMC, the FPGA-based real DRAM chip characterization infrastructure that allows us fine-grained control of the DRAM commands and timings, as well as a temperature controller, so we can control the temperature of the DRAM chips. And we characterize a large number of DRAM chips from all three major manufacturers and spans different die densities and die revisions. So we have two major key takeaways from this work. First, RowPress significantly amplifies DRAM's vulnerability to disturbance by, as we have seen, significantly reducing the minimum number of activations needed to induce the first bitflip. Second, RowPress has a different underlying mechanism compared to RowHammer. So the key characteristics of RowPress on how it amplifies disturbance can be summarized in this figure. So here on the x-axis, we have how long the DRAM row is kept open. And the y-axis, AC min, is the minimum activation count on the aggressor row. You need to induce the first bitflip. And we also investigate two access patterns. The blue boxes represents the double-sided access pattern where we sandwich a victim row in between two aggressor rows. And the orange boxes is the single-sided pattern. So as we can see, as we go from left to the right, we keep increasing the time that a DRAM row is open, and we have orders of magnitude reduction in the minimum activation count you need to induce a bitflip. So in more realistic cases, let's say 7.8 microsecond, that's your refresh interval. So that's the time interval between two refresh commands. And also 70.2 microsecond, that is 9 times 7.8 microsecond. So that's the maximum amount of time that you can postpone your refreshes, because in many cases, your memory controller wants some flexibility or some deadline guarantee in scheduling your DRAM commands. So JDEC standard actually allows you to postpone some refreshes, which gives you much longer time that you can theoretically keep the DRAM row open. And yeah, as we discussed in extreme cases, let's say if we keep the row open at 30 milliseconds, then only one row activation, as like this dashed box shows, is enough to cause Bitflips. Yeah, and we also show that RowPress gets much worse as we increase temperature. It's different from RowHammer because it affects the different cells compared to RowHammer and retention failures. And it behaves differently as we change access pattern and temperature compared to RowHammer. So let's just give an example. A very interesting phenomenon of RowPress is that as you keep increasing the time that your aggressor row is open, up to a certain point, then your single-sided RowPress pattern becomes much more effective at inducing Bitflips compared to double-sided RowPress pattern. This is like an opposite to RowHammer, where in RowHammer, if you do a double-sided pattern, it's always much more effective than the single-sided pattern. Yeah, so this shows something like underlying is different between RowPress and RowHammer. So we demonstrate RowPress Bitflips in a real system. So we use some recent Intel processors and recent Samsung DDR4 module. And note that this Samsung module, it already has the, let's say, the industry's RowHammer mitigation called target row refresh. So basically, it has like some counter tables in the DRAM that kind of keeps track of which rows are activated the most, and then it will send those like victim row refreshes to those potential victim rows. So we have a proof of concept program on this system. The key idea of this program is to keep accessing different cache blocks that belongs to the same DRAM row, so that we can kind of force the memory controller to make that row stay open for longer period of time. So we talk about this briefly in the first part of this lecture, that the memory controller has a row policy that basically decides what you will do after opening a row. So some like basic ideas that you want to keep the row open a bit longer, anticipating for future row hits. And a very popular row policy is called like adaptive row policy. So the key idea of that is like if you have recorded a lot of row hits in a bank in the past, then you just infer that, okay, I will keep seeing more row hits in the future. So the memory controller can choose to keep the row open longer. So what we do here is we keep accessing different cache blocks that belongs to the same aggressor row, and we keep doing this. We generate like a lot of row hits, so we cannot train the memory controller to think that, okay, I should keep the row open longer because there will be many row hits in the future. And by doing so, we effectively increase the row open time, which leverages RowPress to induce more Bitflips with fewer aggressor activation counts. Yeah. So here, like this, like num_read variable just like kind of controls how many different cache blocks we access in a row, which can roughly translate into like how long the row is kept open. So we like kind of like tested 1,500 arbitrarily chosen victim rows, and we plot like the total number of Bitflips we get on this real system in the figure. So here the plot on the left shows the total number of Bitflips we record in these 1,500 rows. The x-axis is like the num_read parameter that we seen just before, which can roughly translate into how long the row is open. So we see that like the more you access in the same row, the longer you kept the row open, the more Bitflip you will see. But like, yeah, in this example, like we don't see, so we see like a significant increase from 32 accesses to 64 accesses, but then we suddenly don't see any future Bitflips if we go beyond 64. So reason for this could be that, let's say if your row is just like open for too long, then you probably don't have enough activation counts to induce the Bitflips. And also, similarly to the total number of Bitflips, we see that on the right, we should plot like the number of rows that contains Bitflips. It also increases significantly as we increase the amount of time that the row is open. So we conclude that by leveraging RowPress, we can induce Bitflips when RowHammer cannot. And note that like if we just access one cache block per aggressor row, then this program does like the same as RowHammer, as like the blue text marks here. Yeah. So in order to mitigate RowPress, so we propose a methodology that adapts existing RowHammer mitigations to also mitigate RowPress. So the key idea is that we will first limit the maximum amount of time that the row can stay open. This is like should be well below the maximum row open time specified by the JDEC standard from the refresh timings, and this like can become like a knob that we can tune to balance between the performance overhead and the aggressiveness of the mitigation mechanism. And then based on this configured maximum row open time and the corresponding minimum aggressor row activation that you need to induce the first Bitflip, we can just configure the existing RowHammer mitigations to work at this point. And by basically increasing the aggressiveness of your RowHammer mitigation mechanism with the knowledge of how RowPress will amplify the redisturbance of the DRAM chip at this point, we have a mitigation mechanism that can mitigate both RowHammer and RowPress. So we evaluate this proposed mitigation by applying this methodology to two popular RowHammer mitigation technique. One is called graphing, and this is like it's kind of similar to the industry TR mitigation, where like it keeps a table that tracks the most activated rows. And second is para, which we already discussed. It's like the probabilistic victim row refresh mitigation mechanism. And we use Ramulator, a cycloaccurate DRAM and memory controller simulator to implement and simulate the performance overhead of applying our methodology to these two existing mitigation mechanisms. And we look at the additional performance overhead of this adapted version of the mitigation over their original versions. And we see that by configuring the mitigation to be like kind of like a sweet spot of the row open time, we can achieve small additional performance overhead over the original mitigations that only mitigates RowHammer. Yeah, so we also have more results in the paper and also the archive version. We have the code to do these, both the FPGA-based characterization and the real system demonstration in this GitHub link. So if you're interested, you can take a look and maybe try this out yourself. And to conclude, yeah, we demonstrate and analyze RowPress, a widespread redisturbance phenomenon that causes bitflips in real DRAM chips by characterizing RowPress on a large number of chips from all three major DRAM manufacturers, we show that RowPress significantly amplifies DRAM read disturbance by reducing the minimum activation count to induce the first bitflip by 1 to 2 orders of magnitude. And it has a different underlying mechanism compared to RowHammer. We demonstrate that someone can use a user-level program that leverages RowPress to induce bitflips much more effectively on a real system. And finally, we propose effective solutions to both RowHammer and RowPress at low additional performance overhead. Yeah. So yeah, that's the end for RowPress, like another aspect to DRAM read disturbance. And of course, like we have many ongoing works, many other aspects, directions to look at in general on DRAM read disturbance. Some of them include, what if we age the DRAM chips? Will RowHammer, RowPress read disturbance become worse, become unchanged, or even become better? And more environment parameters, let's say voltage, more memory access patterns, because yeah, single-threaded, double-threaded, we can have many-sided, let's say. Yeah, and more on how we can design memory controllers and the entire computing systems in general, so we can protect us from the issues caused by RowHammer. Yeah, and I think that concludes my part of the talk on understanding RowHammer and, let's say, hardware errors, read disturbance in general. Is there any question? Yeah, please.
Why physically keeping open the line results in the Bitflips?
Okay, so there are some very fresh silicon level, device level papers that actually investigate this in the TCAD level. So at a high level, so there are like two mechanisms that can cause a victim cell to leak charge. One is, let's say, dominantly in RowHammer, that if you keep like opening, closing a row, then when you close the row, some of the electrons that are there in, let's say, the channel of the access transistor, when you open it, because when you open the row, there are like current that flows, there are electrons that moves between the capacitor of the cell and the bit line. When you close the row, some of these electrons, they can drift towards the victim cell. They can be, so when the row is open, they can be trapped by the interface traps in the access transistor. When the row is closed, those trapped electrons, they are released, and those can also migrate to the victim cell. So that's like one mechanism. Another mechanism is that because of the close proximity of word lines to the cells, so in certain locations in the DRAM chip, so yeah, in like these chips, like they have the 6F squared layout. So there are cells that has a word line that passes through the proximity of it, but does not like actually like forms a circuit. But because of this close proximity, when that row is open, it would like just pull the electrons stored in the victim cell away from the capacitor into the substrate. And when that row is closed, not 100% of these electrons pulled, they will return to the victim cell. So that's another leakage. And it turns out that this second mechanism that we just talked about is affected by how long you keep that row open. So that's like one device level explanation on like why are they fundamentally different. Yeah, no worries. Yeah, thank you. Yeah. Yeah, so if, yeah, please.
So why can't we charge the victim rows if we know which ones they are after the close? So we know that these are certain victim rows that we can charge and flip it.
Yes.
Why can't we activate them after we close the initial row which we were trying to do?
Yeah, that's like the key idea of para, right? So apparently, like you cannot afford to, let's say, refresh the victim row every single time you access like any row. Like otherwise, then you're like, for every row activation, you have to do 2 more row activations, which will make your DRAM much slower and consume more energy.
So actually, the next talk that Misail you will dive into that, right?
Yeah. So my colleague will discuss many different RowHammer mitigation techniques that will investigate and explore like these aspects.
I think we can take more questions while Nisa is setting up.
Yeah. I was just... Any more questions? Yeah, please.
Sometimes we're using obfuscation between the. You said sometimes there's obfuscation between the address that is sent to the DRAM chip and the actual physical location.
Yes.
So the address is in the DRAM chip.
Yes.
Okay. When there's that obfuscation, how do you reliably keep the same row open, or generate these one-sided, double-sided access patterns?
Yeah. So we can reverse engineer this mapping. So the way we do it is we do a single-sided RowHammer or RowPress attack. Then for every aggressor row, we kind of like check, let's say, all the other rows. Then we will likely find 2 rows that has the most bitflips. Then we say, to some confidence, assume those are, let's say, the 2 physically adjacent rows. And then we can just like do this many times for many different aggressor rows. Then we can figure out a function that once applied to the row address will minimize the number of rows that are not, let's say, modeled by this function, kind of like that. Yeah, but and then we usually we cannot have like 100% coverage, because in real DRAM chips they are like always like remapped after remapped rows. So those are like usually the spare rows. So the DRAM manufacturers, they do some testing. They find, okay, one row is broken, so I will use a fuse to like kind of hardwire that broken row to another, like a row in like a spare part of the array. So those are the things that we, like that the mapping function cannot cover, but those are very small. So I think in general, we see like about like a couple dozen per like about 64K rows that cannot be, let's say, modeled by our mapping function. And we also see that even for the same, let's say, chip model, but for different instances of the chip, this number also like changes a bit. Then we think, okay, this is like just a result of this like spare row mapping. And for the other, let's say 99.99% of the rows, our mapping holds. Then we assume this is the actual mapping. Yeah.
Okay. Thank you.
Thank you. Yeah, please. Yeah, please use the microphone, thanks.
Does the activation of row for longer interval or longer time cause a security issue?
Yes, so as we demonstrate like with that program on the real system, if you leverage this RowPress property, if you keep an aggressor open for longer period of time, you can induce Bitflips much more effectively compared to RowHammer. That is to say, you can either induce Bitflips while RowHammer cannot because they are blocked by the mitigation mechanisms, or if you kind of like design a very complicated RowHammer mitigation mechanisms that can already bypass the mitigation mechanisms, then by leveraging RowPress, you can induce even more Bitflips compared to just using RowHammer. So yeah, I would consider like the biggest security implementation could be that like you just reduce the number of times that you need to activate a row to cause a bitflip, because that's what most of the mitigation mechanisms they are tracking of. So yeah, if you just use the pattern makes like so that you can induce bitflips below their tracking threshold, then you are not affected by the mitigation at all. So you can like induce a lot of bitflips. Thank you. Please.
Does making the rows wait on each other reduce the RowHammer? If so, why don't they make the rows wait on each other differently? And for for less important information, they just make them closer for density.
So if we are talking about logical separation, let's say we map, let's say sensitive data to some place, insensitive data to other place, or like we force some separation between sensitive data, that's actually like one way of mitigating RowHammer, as my colleague will discuss in the presentation. But if we are talking about physical separation,
Physical in terms of layout, yes.
yeah, that's because DRAM, the industry, they optimize for density. They want to pack as many bits as possible. If you want to separate the rows, it will significantly reduce the density.
Just for the critical information, let's say, for example, the data that we don't want the RowHammer, we make them a little bit larger.
Yeah. So like maybe you are saying like let's say we can partition a DRAM array, so we have one region that has coarser, let's say, distance, another with tighter distance. I think that's like theoretically possible, but like any irregularities in layout will likely like reduce yield. So yeah, it's like this is definitely like a design, but probably the reason why DRAM manufacturer does not do this is because it makes manufacturing really difficult, and also not like I think it needs to go beyond just like increasing the, let's say, the distance between rows, because in the current layout, let's say 6F squared, the way the transistors of the DRAM cells that are, let's say, they have the same column, they share the same bit line, but they are in different word lines. So actually, like the source of those two access transistors, they are just like shared. So even if you increase the distance, you still have like that shared source, which is a path for electrons to, or like all the redisturbance to go from one row to another. So if we want like complete isolation, this will be very, very expensive. I can't think of, yeah.
Okay, thank you.
Yeah, that's a very good question. Thanks. Yeah. Okay, if there's no further question, then I will leave it to Nisa to talk about all kinds of mitigation techniques.
Also thinking about solutions. I think some of you guys would help with solutions even before you got a chance to describe them. So you'll see more solutions.
Yes. Okay.
Thank you.
So hello everyone, my name is Nisa Bostancı, and in this part of this lecture, we will talk about read disturbance related DRAM scaling solutions. We will talk about like mitigation approaches and different solutions that we propose, and other people, other researchers are also proposed a lot of solutions. So we will talk about those. And I will start with a recap. I'm not sure if you need it just because like we just mentioned everything, but let's go over those slides quickly. Oops. Okay. So today's DRAM chips are vulnerable to read disturbance. Yeah, okay. Maybe I'll just recap the terminology, right? In this part of the lecture, we will call the activated row as the aggressor row, and the other rows that are ended up with Bitflips are called victim rows. And we will call the minimum number of activations that causes the Bitflip the RowHammer threshold. So we saw that DRAM chips are getting more and more vulnerable to read disturbance today, and read disturbance Bitflip occur at much lower activation counts now. So this is the first flipping bits paper that talked about RowHammer that showed this high number of activations causing a RowHammer Bitflips. And Hassan talked about two recent works, more than two recent works that showed even lower values. So we observed that the RowHammer threshold has reduced more than 2 orders of magnitude in less than a decade. And this is exactly why we need mitigation techniques against read disturbance attacks that are effective and also efficient for highly vulnerable DRAM-based systems. So again, we will talk about some solutions today, and let's again recap the 2 types of mitigations that we can have. The first one is the immediate solutions that we have that aim to protect the vulnerable DRAM chips that are already being used in the field. So we have limited possibilities for mitigations here because these chips are already manufactured and they're out there and they're being used. So these solutions are mostly patches aiming to cover those. And we will also talk about longer-term solutions that are aiming to protect future DRAM chips. And we have a wide range of protection mechanisms that we can think of in here because we can design the system, we can design the DRAM chips and the interface between those. And basically, we can think of different approaches and use them. And ISCA 2014 paper discusses both types of solutions, and it proposes PARA as the best solution, and it is already employed in the field. So I'm not going to go over PARA again, but the key idea is to, after closing a row, we activate or refresh one of its neighbors with a low probability. And this gives us a reliability guarantee, right? Since based on this probability threshold, we can say that we will have Bitflips less likely if we, like generate a random number after closing a row and decide to refresh victims based on that threshold. And by adjusting this threshold, we can actually have stronger systems or even weaker guarantees as well if you target those systems. And basically, you can configure this defense based on your requirements. And there are 2 advantages of PARA. The first one being that PARA refreshes rows infrequently, which means that it has low power and low performance overheads. And I want you to remember that when this solution was proposed, we were looking at much higher RowHammer thresholds. And that means that we had like less frequent refreshes needed to cover the reliability guarantee, right? And the second advantage is that PARA is stateless, which means that we don't need to store a lot of metadata to understand which rows are being activated or how many times they were activated in the past and so on. So we can implement PARA with low cost and low complexity. And this is why PARA is an effective and low overhead solution to prevent read disturbance errors, at least when we are talking about high RowHammer thresholds. And we saw this picture. This is a real system that you can enable PARA and even configure the probability threshold. And it was proposed in this paper. So the takeaway of the flipping bits paper is that main memory needs intelligent controllers for security, safety, reliability, and scaling. And after that point, industry also proposed some solutions. Halsong briefly mentioned target row refresh, which we will be talking about, and we will call it TRR in short. And around mid-2010s, some of the DRAM manufacturers marketed some of their DRAM chips as RowHammer free because they employed the TRR mechanism. But the details of the mechanism was not public, so we didn't know how it worked. And the researchers, including us, were excited or interested in how it works and if it's exactly or truly secure. And I will talk about this paper called Trespass, which was published in IEEE SMP in 2020. And it is the first work that showed TRR-protected DRAM chips are vulnerable to RowHammer still. So it shows that mitigations advertised as secure are not exactly secure in terms of TRR. And basically, it looks at different attack patterns and tries to bypass the mechanism. And it introduces the many-sided RowHammer attack. So the key idea behind this attack is to hammer many rows to confuse the mechanism or bypass the mechanism by overflowing the counter tables that it maintains. Basically, the tables are not sufficient to keep track of many aggressor rows, and by hammering many rows at once or at around the same time, you overflow those tables and bypass the mechanism. And this paper partially reverse engineers the TRR mechanism implemented in DRAM chips and the memory controllers. And it provides an automatic tool such that you can effectively create many-sided RowHammer attacks that are effective in DDR4 and LPDDR4 chips. And this is an example of the many-sided hammering patterns. The red rows are aggressor rows here, and the blue rows are the victim rows. And what they did in this paper is to increase the number of aggressor rows such that you will have a large number of aggressor rows that will bypass or overflow the tables. And these are some of the results that they showed. And here we see the number of Bitflips they observed with different numbers of aggressor rows for different DRAM modules. And in here, what you can see is after a number of aggressor rows, you actually observe a lot of Bitflips, meaning that you are successfully bypassing the TRR mechanism. And they looked at a lot of DRAM modules that are listed here from 3 major DRAM manufacturers, and they showed that many of them were vulnerable to trespass. And they also looked at mobile phones and found patterns, these many-sided RowHammer attack patterns, that make them vulnerable to trespass as well. So there are these devices out there that you can observe RowHammer Bitflips. They looked at real-world attacks that are based on RowHammer Bitflips, doing privilege escalation or extract and RSA keys, and they checked the time to exploit these and observe that you don't need much time to actually get some keys in real systems when you use trespass or get privilege, root privileges and so on. So the key results of this paper is that there are still a lot of DRAM modules out there that are vulnerable to RowHammer, and even some mobile phones. And this is just a scratch on the surface because this tool is not exhaustive. It doesn't check all patterns out there. And there can be other vulnerable devices that we were not able to find the successful patterns for. So key takeaways are, first, RowHammer is still an open problem, and security by obscurity is likely not a good solution because we didn't know the details of the mechanism, but by devising some attack patterns, we were able to bypass it. And the second paper that I'm going to talk about on this matter is uncovering TRR almost completely. So this is a work from Micro 2021. This is a follow-up work of Trespass. And again, we are looking at the question of, is TRR fully secure, and how can we validate its security? UTRR proposed a new methodology that leverages data retention failures to uncover the inner workings of TRR and study its security. And they looked into a lot of DRAM modules again, and a lot of new RowHammer access patterns. And they observed that there are still a lot of modules vulnerable, and the majority of the DRAM rows in these modules experience at least one RowHammer bitflip. And maybe most interestingly, when we look at 8-byte data words, we see that some of them experience up to 7 RowHammer bitflips, which makes ECC ineffective. So you cannot recover from those. And this work again shows that TRR does not provide security against RowHammer. And it can be used for further research. And they again look at a lot of DRAM modules and observe that they are vulnerable. And after that point, Google actually showed another attack, which is called half double, that leverages another access pattern, basically by hammering a lot of aggressor rows in different places. They were able to observe bitflips. And this was published at Using Security 2022. So we need better solutions. And we will next look at some RowHammer solution approaches. That some of them we discussed with questions. I'm seeing that we're approaching the coffee break. Should I go on, or is this a good place to stop? Okay. Yes.
In that paper that if you activate that aggressor row A many times, and then activate aggressor row B a little bit, you see the B also, right? Then you would cause bit flips in the victim row C. That's interesting, right? The main reason why this is interesting, I believe, is normally a solution like Para or other solutions that people have employed would detect the aggressor row either probabilistically or in some other way. Now, once you detect the aggressor row, what do? You refresh its victim rows. And which row is that? That's aggressor row B. Now the solution itself becomes part of the attack, right? So I think that's the really interesting observation in this Google paper. That basically shows that you should be extremely careful with how you solve the problem. And I think I should also mention that it's great that Google and Microsoft, they both have written multiple papers on this topic. Actually, Microsoft has written probably 5 or 6 papers on RowHammer itself in different ways. Then you may think about why they're actually writing papers on this topic, right? Because they have these huge infrastructures where they have huge amounts of DRAM, and they're very much worried about the integrity of the data that is in their infrastructure that belongs to either them or, in many cases, other people that they promise data integrity for. Okay, so who wants to take a break now? Or do you want to continue? No. This may be a clean place to take a break, but if there are questions, maybe you can ask. Yes, go ahead. I mean, of course, we have tried discussing with DRAM manufacturers, as Nisa will hopefully get to in the later part. DRAM manufacturers did not want to talk about this problem for many years. So they still don't want to talk about the problem much. But they do write papers about it right now, at least. That's the good part.
Do you think they already know about it, but they don't want to talk about it? Or
like they already know about it when?
Maybe the solution is really difficult, or maybe when we make like what happened with SRAM, like we make scaling, we make density very low. Yeah. So the level physically, when we apply a voltage, there will be like quantum effect, like quantum tunneling, or some leakage, like very high leakage. It's complicated to fix it.
I mean, it's no question. There's no question that the solution is very difficult.
So maybe physically, if we find solution, then we'll find out like we have 2 T, 1 C, and then it will be.
Yeah. If you go to different DRAM cell structures, the problem can be alleviated. We're not going to talk about that, but a lot of them are very costly at this point. I think Nisa is going to dismiss them saying it's very costly, which is true. But yeah, I mean, DRAM manufacturers potentially knew about the problem, but I feel their pain also. It's very difficult to really solve this problem once it comes to this level. Now they're trying much harder to provide solutions, but we will discuss some of those when we get to the industry solutions, right, Nisa?
Yes.
And, and the effect of RowHammer, like, is it so dangerous to the level like, I know one attack can make really dangerous things, like if we flip little.
Well, that's what a lot of security people have shown. In the end, I think you should not have these robustness issues. And again, it could be an attack, but as the number of hammers that induce a bit flip reduces, it could be that existing workloads can actually do this, right? If your benign workloads that are not attacks start flipping your bits, then it could be all sorts of safety issues, availability issues that are lurking. That's what people are very much worried about. And if you don't protect against these, who knows what people could be doing, right? I think there could be people motivated enough to launch this sort of attacks. Yeah. I think you had a question over here, maybe. Yeah, maybe we'll take that question and then we can take a break. I've used the last 5 minutes, sorry. Or maybe we can make Konstantinos work more by taking more questions.
But for a pretty short period, and I got my hands on the testing procedure algorithms and the patterns of the really old-ish dynamic memory chips, like before the age of DDR, and with the capacity of only megabytes or even kilobytes. And there used to be a series of mature patterns to test the adjacent bit flip situations or circumstances. But we see that in the age of DDR now, processors are designed to boast many levels of caches, and the DDR controllers are getting much more complicated. This problem showed up again. It's real, as is mentioned by the RowHammer. And from my understanding, it's even not a complicated and sophisticated pattern for the RowHammer. But for now, those DRAM chips are scaled and manufactured as it was with those vulnerabilities. So as you mentioned just now, I wonder if there is just a trade-off or cost-relative selections between being made by those manufacturers on DRAM testing, or even decisions to tolerate those faults. Yes.
Yeah, I mean, that's a very long question, but I think what you're getting at is basically, are DRAM manufacturers cutting costs by not doing enough testing, and as a result, these are slipping into the field? I don't know. I'm not in the shoes of the DRAM manufacturer. I cannot answer that for sure. But I should say that testing for this issue is not easy. So for example, after we published our paper in 2014, by the way, it was rejected first, and then it got published at ISCA. And then 2 out of the 6 reviewers still rejected the paper. They didn't want this published. I mean, they may be from industry. Who knows? I don't know, of course, right? This is double-blind review process. There's a story about that too, which we can get into if needed. But after we published our papers, the first people who picked up on the problem was the Memtest 86 memory tester, memory testing program. I think it's Passmark. They do the Memtest 86. And they added a test specifically for RowHammer. They called the hammer test. Now, the older tests that you mentioned are not exactly testing RowHammer. They're testing adjacent bit flips, but they're not activating rows 100,000 of times. You see what I mean? They're old tests. So clearly read disturbance was very well known in the field, but nobody, in my opinion, was testing for RowHammer until we showed the problem. And then the Passmark software included that test. And if you go to their website, I used to have this in one of my slides. I don't know if you have it, but after they included this test, immediately they started getting complaints from people saying that this test keeps failing. So this test is run when you boot up your system to see if your memory is working well. And a lot of memory started failing this RowHammer test. And they had to update their website saying that these are real errors. This is a known issue. Go read this paper, which is our paper in ISCA 2014. That's how they update it. This is actually on their website still. And so basically people start testing, but even testing is not easy, I would say. So DRAM manufacturers have this pain because testing every single every single cell for RowHammer, basically you need to keep activating everything with different data patterns, worst case data patterns, etc., under different conditions. That's what Hao-Song was referring to, right? It's under different temperatures because different cells are vulnerable at different temperatures also. So testing for RowHammer is a very complex problem. And I know multiple people who do very good work in the VLSI testing community try to look into this problem and conclude it the same way. It's still good to think about how to test for this. Okay, any other questions, or should we take a break now? We should probably take a break and then we'll continue.